Hey everyone, welcome back. So this video is in continuation with our system design series course. And in this video, we'll be covering back of envelope estimation, also known as capacity estimation, where we'll see QPS, storage, and bandwidth maths for system design interviews. And believe me, this is a very important concept and very important part of your system design interview. This part especially comes after your functional and non-functional requirement ends. And here's why this matters. So in most of the system design interview, right after your requirement gathering, the interviewer expects you to do some estimations phase. I mean, how much QPS you can handle, how much storage you would need, how many servers you would need. And this takes roughly around 2 to 5 minutes. And it's not optional. Everyone should do it. I see a lot of candidates skipping it. But no, this is a very important part of it. Because every decision you make after this maths depends what kind of architecture you'll be building on the top of it. So whether you need a cache, whether you shard your database, whatever you need, like how many CDMs, how many server, all that comes from this number. So if you skip this estimation and you directly jump straight forward into drawing boxes, that is your guessing, right? And the interviewers can tell that you skip the capacity estimates, which is a bad sign. But the good news is it's very simple maths, nothing complex. You can literally memorize like about 5 numbers and some of the formulas, and that's it. So here is what we cover. We'll cover those numbers that you need to memorize, some of the formulas to do back of the envelope estimation from QPS to get the storage, the bandwidth, cache sizing, and then we'll apply all these numbers into two real interview questions. I mean, if you have given, let's say, to design URL shortener or to design Google Drive, we'll use that these two systems problem to apply whatever we have learned so far. So let's get started. So the very first part of this is some numbers that we need to memorize. I mean, you just need to memorize this, and then the QPS maths become easy peasy. That's it. So 1 day is equal to, as you know, we know it's 86,400 seconds, but we'll round it off to 10 to the power 5, which is like 1 lakh seconds. And you might ask why? Because it's easy to remember, right? I know it's just some percentage off, which is maybe could be 15% off from 86,400. But this is easy to remember. Now you know 1 day is equal to 10 to the power 5 seconds. Just hold with me and you'll get to know why we are remembering these numbers. Now 1 month become 3 into 10 to the power 6 seconds. Once you remember 1 day, you can just multiply it with 30 and you get this number. And you can always safely say in interview, hey, I'll assume that 1 month is 10 to the 3 into 10 to the power 6, which is mostly assumptions. And back of the envelope estimation is mostly assuming some stuff and then building on the top of it. And then 1 year becomes 4 into 10 to the power 7 seconds, which is 365, got round off to 4, and then multiplied with 10 to the power 5, which becomes 4 into 10 to the power 7 seconds. I don't know why I need to explain this math, but it's straightforward. But all this maths, especially for the day, 1 day, it seems a 50% off, right? But it's fine because your inputs are also 30 to 50% decibels. Because your interview might say, you can safely assume that your daily active users are, let's say, 1 million, or your monthly active users are, let's say, 50 million. So it's all guessing. So if we don't know the exact QPs that we might receive, then we can do some sort of estimations to get, because in interview you can't do exact maths. So you can do just best effort maths. So rounding off 15% like invisible to whatever we are guessing for such a large scale. And that's it. Let's move to the second part. Power of 2. So the thing is, computer understand in the power of 2s, right? And here we count in the power of 10. And I mean, if we can bridge between power of 2s and power of 10, it's easy to remember for us, right? And why do we need that? We'll see how. So 2 to the power 10 becomes 1000, which is 10 to the power 3. And you might now ask, 2 to the power 10 is like 1024. 1024 becomes 1 KB, right? Correct. So 10 to the power 3 KB. So 2 to the power 10 becomes 10 to the power 3 KB. 2 to the power 20 becomes 10 to the power 6, which is now MB. 10 to the power 9 is 1 GB. 10 to the power 12 is 1 TB. And 10 to the power 15 is 1 petabyte. And now you see the difference, right? Because computer counts in the power of 2. And humans, we understand the power of 10. I mean, we do understand the power 2, but it's not obvious and straightforward. And by accident, you might say that 2 to the power 10 is 1024, which can be roughly estimated as 1000, right? Which is just 2% off from the real answer. So every storage unit steps something like this, which is like you keep multiplying by 10 by 1024 number, right? Which is like you keep multiplying 2 to the power 10 to get the next. So now it's easy to remember, right? So let's say how many 1 kilobyte 1 million user will consume. So you can just simply multiply. You can just simply multiply these two exponents. So 1 million user, if each one user is consuming 1 kilobyte of data, it would be 10 to the power 6, which is 1 million, into 10 to the power 3, which becomes easily 1 GB. And these maths you can do instantly in during interview. Nothing to remember all those complex number of 2 to the power 10 to the power 20, nothing. So no long multiplication, no counting zero. That's the whole trick. Simple. You keep multiplying and adding the exponent 10 to the power 6. So the base number you have to remember 10 to the power 3, which is 2 to the power 10, is 1024 and becomes 1 KB. And then if you want to go further, you multiply it again 10 to the power 3, it becomes MB. You multiply 10, sorry, you multiply 10 to the power 3 again into 1 MB by GB. You again multiply 10 to the power 3, you get TB, and so goes on. So the next very important concept here are these classical numbers for latency. And these are derived from this GitHub repo. It's a very popular GitHub repo. You can check it out. I'll put the link in the description. It's called Napkin Match. So these are the classical numbers, was coined by Peter. And it's all called Peter's list and was popularized by some Jeff Dean at Google. So we'll see what are these numbers, right? So basically, these are the latency. I mean, how much time it would consume if you seek data, if you read data from an L1 cache, branch misprotect, L2 cache, mutex lock, main memory. If it compresses 1 KB, if you send 2 KB over 1 Gbps speed, so it's like how much time it will take, like 0.5 nanosecond, and it goes on increasing. Main memory reference, if you're doing it could consume 100 nanosecond. Similarly, if you're reading from SSD, it's 150 microsecond, and it goes on. And if you do cross continental round trip, which is like from India to North America, it might take around 150 milliseconds. Any round trip within the same data center will be fast because both of the data centers are not overseas; they are in the same country. Let's say one in Kolkata and one in Delhi, so it will take less time for the round trip. Would be just 0.5 millisecond. Also, you don't need to memorize this thing, right? Because the only thing that you need to remember are these four ratios. One is that RAM is 1,000 times faster than SSD. That's it. Just remember this. RAM is 1,000 times faster than SSD. That's it. And now you know answer why caching is fast. That's the entire justification. Why we bring out data from our main memory and keep it in RAM, which is essentially cache. So every time you add Redis, this is what you need to put because RAM is 1,000 times faster than SSD, our main memory. Then within same data center, the round trip cost 0.5 millisecond versus the cross function cost 150 millisecond, which is like 300 times. It's a very worse call, right? So one cross region call in the hot path eats most of like 200 millisecond budget. Let's say you have to let's say finish your API call within 200 millisecond. So only the cross continent call. Let's say you have to send some data from North America to India, or maybe read some data from North America data center and bring back into your India data center. That would essentially cost most of your latency budget. And that's why we use CDN and geo replications, and we shard our data into different geos. Now you know the answer. Why do we do that? Also, sequential reads are far better than random reads. A disk seed is around 10 milliseconds, and reading a whole MB in order is just 20 milliseconds. But jumping around costs more than reading sequentially. So that's why Kafka append only log and LSM trees are very fast, because sequentially reading is very fast than random reading. Then compression is nearly free. Yep, 3 nanosecond to compress a kilobyte versus 20 microsecond to send 2 kilobytes. So always compress before you ship your bytes. So always compress your data, then send it over network, right? Because compression is very fast, very fast. You compress it quickly and then send over. I mean, you will send now smaller data and then you can uncompress at the client side or whatever side you're sending it. So basically encrypt and decrypt and compress. Okay, this is very important concept called availability table, and I've talked about it in one of my previous video where I was talking about availability. And this is just math because the year has around 8,760 hours, and you keep multiplying it with the percentage that you're missing. So let's say you say your SLA budget is 99%. I mean, you're targeting 99% of uptime, which is your system is mostly available for 99% time, which means only 3.65 days you can afford to lose, which boils down to 15 minutes per day. That means only 15 minutes per day you're saying that my system can go down. If it goes more than that, your SLA availability drops. And now let's say 99.9, 8.7 hour, then per day downtime you can afford is 1.5 minute. If it goes further, it reduces further. So 5.9 availability, which is essentially, you see the 5 nines, right? 99.99. This is the SLA that big tech companies like Netflix, Google, Amazon, they target, which is just 5 minutes of downtime. I know this is impossible to achieve, but a lot of companies do target this, which is essentially only 1 second of downtime per day. And this 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 is crazy because extra 9 means 10 times less downtime. See, 10 times less downtime, which means roughly 10 times more engineering cost will come. That's why this big tech company, they are paying a lot to maintain their servers, to maintain their systems, because it costs a lot of pocket and lots of money out of their pocket. That's why their subscription models are so high. Multi-region deployments, automating in fact, automated failovers, and also the no maintenance windows. Because if you're targeting 5.9, you just have 5.2 minutes per year to maintain. You can't go down. So in an interview, it could be payment needs 4.9. I mean, any payment gateway, let's say API gateway or payment gateway. So no single region is off the table. Everything is here. So that's the SLA number that your interview might ask you to threat on. Yep, we already discussed. One extra 9 means 10 times less downtime, which is almost 10 times more engineering cost. Now, let's remember these four formula. And this is the entire cheat sheet, and everything else is just multiplication. I'm not kidding. Or maybe by the end of it, you can take a screenshot of it and maybe print it out and keep it in front of you so that you read every time. Or maybe you can bookmark this video and come back and always read this four formula, which is very, very important. QPS, average QPS is simple. QPS is queries per second. Some people say TPS, transaction per second. Some people say RPS, request per second. All fine. I call it QPS. Average QPS is nothing but daily active users. Let's say your daily active users is 1 million, and you only multiply it with how many actions they're taking, how many get calls, read calls, could be, let's say, 2. Then you multiply it with, and then divide times by 5, you get the average QPS. Peak QPS, we take a multiplication factor of between 2 to 3. You say, let's say, if your system is averagely seeing 1K QPS, then you can assume your peak QPS could be 5K or 3K or 2K, whatever. You can discuss it with your interviewer. And then read QPS is nothing but your write QPS multiplied by read to write ratio. Let's say, I'll take an example of URL shortener. I already have a video on it, and I already talked about all these things. Let's say your read to write ratio is 1 to 100. So a user is only creating one URL but reading it 100 times. So your read to write ratio is 1:100. It means one write, for every one write, there's 100 read. So the read QPS would be simple, right? You multiply the write QPS, which is 1, into read to write ratio, which is 100. So it becomes 100. That's it. Storage. To get the storage, this is a very important formula that you need to remember, which is writes per day. How many writes you're doing per day into object size. Each object size, let's say 1 KB, into retention days. I mean, for how many days you want to store it, let's say 10 years. And then multiply with replication factor, because you might be storing the same data into multiple charts. I mean, multiple databases, so that if one database goes down, you have others where your data is already there available. So which is called replication factor. I mean, you copy those data into different databases. So let's say you copy for 3, or this replication number could be anything, but in an interview, 3 is a good choice. I mean, we'll do all this maths with some of the examples in the next slides. Then the bandwidth, ingress and egress. Ingress is the incoming QPS, I mean, all the writes QPS to your server, multiplied with average upload size. Let's say S3. For S3, AWS S3, or for GCS, Google Cloud Storage, which is essentially S3 only. The ingress would be how many QPS, how many people are essentially writing at the same time into average, multiplied with average upload size, could be 1 MB or 1 GB. The egress is how much people are reading from it, multiplied with what is the average size of the read. The cache is 20% of your daily hot data. That's it. And RAM is costly. It's not cheap. So we do some good maths and understand and see what hot data we have, and we basically what kind of data is repeating, what kind of data is being read more. We bring out from our DB and put it on cache because it's faster to read. You skip all the DB calls. Now say each one out loud. This is very important. Think out loud. Don't just assume. Think out loud, please. DAO from a daily active user from monthly active user. I know it's very simple maths, but yes, if given monthly active user, so let's say if your monthly active user, because these are average, let's say monthly active users are 100 million, then you can say 25 to 50% of it would be daily active, right? And you can again correct this assumption with an interview. Peak factor, which is like whatever traffic you're receiving on an average, you multiply it with some number, let's say 2, 3, 5, and then determine what would be my peak factor of it, right? Let's say for IPL matches, flash sale, ticket drops on BMS Mumbai show, the peak could be anywhere between 5 to 10x traffic that you might be receiving earlier, I mean, before this event. So you always design for peak, not for average. Remember this. No one is asking you to design for an average QPS that you might be receiving, because your system should be resilient and robust enough to maintain the peak traffic. The peak traffic in lead code would be the contest. In the first 5 minutes, lead code would see a surge of submissions, and after that you could reduce it. So it has to prepare itself. Read to write ratio, we have already discussed this. I mean, how many reads and how many writes from your average traffic. You can derive this number for last 1 month or maybe last 1 year. You can do this average and see how much read our system got and how many writes we got, and then get the ratio. For URL shortener, it is like 1:1,000 or 100. The next very important concept is sizing DB objects properly in an interview, because this is where most of the estimates go wrong before even the math starts. And be honest about it, okay? Because let's say Twitter, 280 character tweet. It's not 280 bytes, right? We add user ID to it, commit timestamp, messages, indexes, and now you are at around 500 bytes. So whenever you're unsure that how much object size that you're dealing with, always do assumptions, honest assumption, and round it to 1 KB safely. I do it very often in interviews. I say, okay, worst case, we'll have 1 KB of data storing. That's it, fine. Because essentially it's not 280 bytes when we talk about 280 character tweets. So when ensure, round the text records to 1 KB. Now let's split the text from media, because media data you should always like consider apart from the text. So media is typically 100 or 1,000 times larger than your text. You got a text story, right? The blob. And that will dominate your storage numbers as well. So these are very two different numbers. Now, this is again going to be very important. Server capacity numbers are also important. I would say these are cherry on the top things. And if you discuss kind of things, your interview will be just damn blessed. One app server or one single machine where your code is running, let's say your Java binary is running, can handle 1,000 QPS or RPS. Assuming that's a 8 core machine, I mean, you can do this back of the envelope maths. If it's a 8 core machine that's running your API code, where each request does some real thing like authentication, DB call, JSON serialization, and all these things consume some milliseconds of CPU, it can easily handle 1,000. I mean, considering the situation, your one server can easily handle 1,000 QPS. Let's say if you handle 300K peak QPS, you will need 300 such instances of it, and then you load balancer so that you can divide the load. Now you know how to do the back, right? You might be thinking, how do I decide how many servers do I need to handle this thing in QPS? From this maths, you can do, and you can learn this maths, understand this, and put it in your interview. One SQL database can handle easily from 1 to anywhere between 1 to 5K writes. I'm not talking about reads. Reads is much higher than this. And typical PostgreDB, because I work with Postgres, with indexes and locks, can easily do that. And reads go much higher than this. Much higher than, I would say, at least 10 times. Now, one Redis node, again, because we're talking about caching, can easily handle with one single thread of Redis. I mean, Redis is like single threaded, can handle 100K operations per second. That's crazy. All from RAM, single threaded loop. So 1 million read QPS, you would need just 10 Redis node. 10 Redis node, that's it. And you can again talk about it in an interview. Now, that's the time. And also, I forgot adding, Google search is around 100 to 200 QPS. I mean, it receives 100 to 200 QPS, which is like around 2 lakhs of concurrent Google search requests. And now imagine how it would be dealing it. Okay. Now let's discuss whatever we learned so far. Let's try to implement this. Example one, which is URL shortener. And I already have a video on this. You can go and check it out. Don't assume. Don't assume in your head. I mean, if you're assuming something, put it and then write it and then think out loud and tell your interview. I mean, exactly like an interview, you have to follow this. And this is like would be like interview scenario. And you'll do some assumption. You say, or maybe this assumption would be thrown by your interviewer. And you say, okay, hey, Anubhav, for design URL shortener, you can assume that you'll have 100 million new URLs per day. I know I've taken insane scale. This is just to show the maths. In a rare interview, it would be around 1 million new URLs per day, or maybe 10 million in a month. Like 10 million URLs are being created in a month. But for doing good maths, I've taken big number. And then read to write issues 100 to 1, which means for every one write, there's 100 read. And retention is 10 years, that you want to store this data for next 10 years. And each record will consume around 500 byte, but we can safely round it to 1 KB. That's fine. Now, nature of the system. From this assumption, we can see it's write light because we are writing very less, and we'll see how much QPS we'll see for writes. But it's read heavy because the read to write ratio says that 100 times more than writes. And tiny storage objects, and 1 KB is very less. It's fine. Now let's do the maths. From all these assumptions, we'll try to find the write QPS. And write QPS is what? 100 million is 10 to the power 8. 1 million is 10 to the power 6. So 100 million becomes 10 to the power 8. You divide it with what? QPS. Basically 10 to the power 5, you get 1K QPS, and the peak becomes 3K. Let's say I multiplied by 3. You can say, okay, the peak write QPS could be 3K. Remember, why did we divide it by 10 to the power 5? Because we want what? Per second. And in one day, we have 10 to the power 5 seconds, right? So 100 million new URLs per day, 100 million divided by 10 to the power 5, you get 1K QPS. Peak is 3K. I hope you get that number. Read QPS is again simple, because you know this, that read is 1,000, which is this 1,000. You got it from there, just above 1K. You multiply with 100 because the read to write ratio is 100. 100 is to 1. You get the read QPS is 100K. Yep. And the peak would be 300K. 3 lakh. Now, very important part, storage. How much storage you would need for this? 100 million new URLs per day multiplied 1 KB because that's what we rounded off. Then multiplied with how many days you have into 10. Then into 3 because 365 is like 1 year multiplied with 10 becomes 3650 because you want to store it for next 10 years. And 3 is the replication factor because you want to store this data into different databases so that you bring up the availability. One node goes down, you have two other two become the master, which becomes around 1 petabyte. Yep. Even during interview, you can round it off 3650 to 4000. Easy multiplication, right? Then DB rows over 10 years. How many DB rows you will consume, which essentially becomes 4 billion. And then how many shortened code you would need because you need the ID spaces. I mean, you need to store this. How many IDs, how many character IDs are enough? I mean, this is literally off topic, but if you watch my interview, if you watch my UL shortener interview video, you'll get it. Talking about the ID spaces, that would be 62 to power 7, right? Because we need around 4 billion DB rows over 10 years, we will need that many unique IDs because we are converting long to short URLs. So since we use base 62 encoder, so 62 to the power 7 becomes 3.5 trillion, which is much more than what we required. 7 characters enough here. Now, next example. Second example is Google Drive, very important. And this example is already understanding now. Assumption, again, we start with assumption. 50 million daily active user. 2 files upload per user per day. So each user, on an average, daily uploads 2 files, which is true. These all are the realistic numbers, not some fancy numbers. Average file size is 500 KB. Good assumption. Read to write is 1:1. I mean, whatever. It's like reading your writing. I mean, we are reading whatever we are writing. That's it. Now let's do the maths. 50 million daily active user into 2 uploads becomes 10 to the power 8 uploads per day. Huge. Right QPS becomes 10 to the power 8 divided by what? Again, we remember 1 day, seconds in a day is 10 to the power 5. We divided that, we got 1000 per second, which is like 1 QPS, and the peak become 3 QPS. Ingress, because we are storing data here. Storing and reading. Ingress is 1000. We remember the formula. I will go back again. Here, remember the ingress formula. Write QPS into average upload size. Ingress is write QPS, which is 1000 multiplied average upload size, which is 500 KB. You got 500 MB per second, which is roughly 4 Gbps. Storage per day comes out to be 50 TB per day. Storage per year comes out to be 50 TB into 365 into replication characters, somewhere around 55 petabytes. I haven't added the egress cost. I will ask the viewers to put in the comments. Now, similar QPS to the URL shortener, but a totally different story. I mean, same 1000 writes per second, but completely different system because the object is 500 times bigger. Remember, in our URL shortening, it was just 1 KB. Here it is 500 KB, 500 times bigger. Things changed. So always ask during an interview, what numbers dominate? Like, is it the storage? Is it the, I mean, it's the read or the write? You need to ask such kind of clarification questions so that you will get this assumption numbers from your interviewer, or maybe at least get a green flag if you're doing yourself that assumption. So here QPS is dominant. You see QPS is not that much, but storage and bandwidth dominates. So your system needs to focus on how to efficiently store these data and essentially retrieve the data, which is an egress, how easily the user is able to read the data and write the data because QPS is less. Now every system lands in one of these 3 bucket, and this is my way of understanding systems, and this is how I find it out what kind of system I'll be going to build within like 5 minutes of your interview. Read heavy tiny objects. Your system is read heavy. Example, your shortener, Twitter timeline, newsfeed. It's read heavy. Mostly people are reading, not writing. And cache is the design. You need to cache. Whenever your system is read heavy, you have to identify where I can do the caching. Then storage and bandwidth heavy. Just we saw Google Drive, YouTube, Netflix, Dropbox. Yeah, all these are storage and bandwidth heavy. You need to focus on blob storage, CDN, dedupe, delta sync, DB holes, and metadata. All this kind of terminology you need to take in mind while designing. And then read heavy streams. I mean, read heavy systems like chat, metrics, logging, event digestion, Kafka. Then comes abandoning logs, which is essentially Kafka, sequential IO, message queues, RabbitMQ, these kind of things. Now it's your turn, guys. If you have made the end of the video, I'm very happy for you. Pause the video and answer in the comments. This is given 100 billion messages per day, and this is real numbers. Each message around 100 byte, read write is 1:1, 1030 is retention, and replication is 3. Safe assumption. And you have to compute what? Write QPS and its peak, total QPS, 3D volume, 30 days for storage, and which of the 3 shape it's get into. We just discussed it, these 3 shape. And also ingress and outgress, if it applies. Bonus, can you check your total QPS against Google search QPS? Why? Because this is a very good system that we can compare with Google search. Something interesting happened, and I want you to tell me in the comments. Now, a very important part, take a screenshot of it, or maybe just store it somewhere or bookmark it. This is a sticky note that you need. Screenshot it, that's it. And now we are at the end of the video. And I hope you liked it. I know this was a little bit long, but you can watch it at 1.5x. and finish it. Thank you so much for watching, and comment down what video you want me to make next. Thank you. Bye. Take care.